Hello there, it's a while since I've done this, but here we go. So we're going to talk about mechanics and the next part of mechanics. And the great news about most of the mechanics we do this year is it really isn't hugely different from the stuff we did last year. And for those who do physics, it is very much an overlap of what you've done. So the first thing we need to talk about is forces at angles. And so here we've got a force of 15 newtons acting at an angle of 30 degrees to the horizontal. Now, where you have forces acting at angles, it's just a complication. Last year we talked about things moving horizontally, cars towing trailers and things like that. Or we've talked about things going vertically, so projectiles being fired directly upwards. That just makes things really easy. As soon as you get an angle, it's a bit complicated. But we make it simple by saying, what's the effect of this angle in the horizontal direction? So we call that resolving horizontally. And in the vertical direction, resolving vertically. And we work out those two effects separately. And we use trigonometry for that. So to work out the horizontal effect of this force, we say, okay, it's that. I'm going to call that x because it's in the x direction. And so hopefully you can see that because we are dealing with a right angled triangle and we've got the adjacent and the hypotenuse, this is a cos problem. So we've got cos 30 degrees is equal to x over 15. So x is 15 times cos 30. So the horizontal component of that force is 15 cos 30, which we could work out on a calculator. Now the vertical component is this, and we could draw a right angle triangle like that, but hopefully you can see it's the same as the opposite side in the triangle we just had. So this and this are the same, and it just perhaps helps to stick with the same triangle. So let's call that y. And this is still 15. So now we're dealing with the opposite and the hypotenuse, so it's now a sine problem. So the vertical component is 15 sine 30. And that's a really key thing to understand when you've got a force at an angle. If you know the angle between the force and the horizontal, then the horizontal component is 15 cos 30, and the vertical component is 15 sine 30. Now, the other way we could do it is we could say, well, if this angle's 30, this angle is 60, and we could say, well, that's the angle adjacent to that 60 angle, so we could say it's 15 cos 60. And I have a feeling when we did moments, I might have used that way myself, but having chatted to physics teachers, I know they use cos and sine, so I'm going to try and do the same as them. So we could think of this force as being 15 cos 60. I'm going to call it 15 sine 30. So basically, if you know the angle, it's cos. So I knew the angle between the force and the horizontal here. And if you don't know the angle, so I don't know this angle here, but that angle's 30, then it's sine. We'll get used to it. I promise you we'll get used to it. So where we have a combination of forces, we get one of two things. We either get equilibrium, because the two forces cancel each other out, or we get a resultant force. So let's look at a couple of examples where there is a resultant force. So we're going to work out the resultant force in this situation here. And we're going to do it by doing the two components, horizontal and vertical. So resolving horizontally firstly. Well, this force is already acting horizontally, so that's still 20. And this force is at an angle of 30 to the horizontal, so that's going to be 15 cos 30. I want to know the horizontal component, and I know the angle between the force and the horizontal. And resolving vertically? Well, this force here has absolutely no effect vertically because it's at right angles, it's perpendicular, and you may remember that from last year. Where we have forces that are perpendicular, they have no effect. This is not going to have any effect up or down. So the only force we've got is the vertical component of this. Now we don't know this angle here, so it's a sine one. So we do 15 sine 30. Or we could have called it 15 cos 60, because that angle there is 60. Now, if I work those two out, make sure you're in degrees for this. So I've got 20 plus 15 cos 30. So let's say that's 33.0. And 15 sine 30, well, I know one of them is going to be a half, so it must be that one, so that's 7.5. And you may remember that the other way of describing that, so what we've basically got is we've got a resultant force of 33 newtons horizontally and 7.5 newtons vertically. And you may remember we were able to describe that using vectors. So I could say, right, the resultant in this situation is this, which is a column vector where this is the x and this is the y value. But you may also remember we used I and j notation. I is a force of 1 newton in the horizontal direction, and j is a force of 1 newton in the vertical direction. Actually, they're not just used for force. It depends on what we're dealing with. It's a unit vector. It's 1 unit in the x direction, 1 unit in the y direction. But this is another way of describing the resultant force as a vector, a combination of the x and y components, and this is it written as separate horizontal and vertical components. So pause the video and tell me about the horizontal and vertical component of these two forces, the resultant force with these two forces. Okay, so resolving horizontally, these two forces were opposing each other. So I was saying, right, to the right is positive, doesn't actually matter, but that's the convention. So this force horizontally is 12 cos 50. I know the angle from the horizontal, so it's cos. But this force, which is 9 cos 35, is acting against it. So it's that, take away that. And they almost cancel each other out, but there is an effect in the positive y direction, positive x direction. However, when we can resolve vertically, they're both going in the same direction. And we don't know the angle with the vertical, so it's sine of the angle with the horizontal. 12 sine 50, that's the component from this one, and 9 sine 35, which is the component from that one. And I can write that in vector form. Okay, so when we've got a combination of forces and they are not in equilibrium, there is a resultant force, we can consider what the overall effect of that is. So, in fact, I'm going to take it away. So let's take this first example. Can I tell I'm rusty? I'm all over the place with the camera. So in this first example, the net effect is a force of 33 newtons in the x direction, so let's draw that, and 7.5 newtons in the vertical direction. So what's the combined effect of that? We've got these two forces, what's their combined effect? And most importantly, what direction is that going in? Well, again, you will remember, hopefully, this from last year, where we've got any vector, we can work out the magnitude and direction of that vector. The vector has broken the force down into horizontal and vertical components. So if I want to work out the magnitude and direction, it just is a Pythagoras and a trig problem. So I'm going to work out the length of the hypotenuse, which is just the square root of those two squared. So that is 33 squared plus 7.5 squared. And I realise I'm using rounded values, bad maths, I realise. But there we go. So that's 33.8 newtons. And then the angle is, I know, opposite and adjacent, so that's a tan problem. So tan theta is 7.5 over 33. So theta is shift tan of 7.5 over 33. And we normally work in degrees, so that's 12.8 degrees. So the overall effect of those two forces in combination, we worked out the components, and we've said, right, so the overall effect is a force of 33.8 newtons in that direction there. That is the resultant force when those two forces combine. The resultant force is a force of 33.8 newtons at a direction of 12.8 degrees. So do you want to work out the resultant force of our second example? We've got the horizontal and vertical components. Pause and have a go. Okay, so we earlier worked out that the result of those two forces acting together was that in the horizontal direction, that in the vertical direction, which we wrote as a vector. But if we consider the combined effect of that, we use Pythagoras to get the magnitude of the force, and the angle is 88.6. Okay, so a little bit of practice. If you are using the online version of the textbook that I showed you how to get to on the CGP website, it's page 81, exercise 5.1.2, question 1, just do a few of those. If by the time you watch this the paper copies have arrived, hopefully they will have done, then it's the same exercise is on page 110, exercise 5.2. All of those are combinations of forces which have a resultant force. Okay, so we've talked about a resultant force, but what about if we're dealing with a particle? So I really should say, I've said this earlier, there's some sort of particle here. What if we're dealing with a particle that is in equilibrium? And that means that the resultant forces are zero, they cancel each other out. So here I've got two forces that I know and one that I don't know. And to work it out, well, I can either work it out horizontally or vertically. So let's go with horizontally. So if I consider the horizontal force, I've got 5 newtons actually in the horizontal direction, but then I've got two forces acting against it. So I've got 4 cos 60, and I've got Q cos 70. And because they're in equilibrium, that's going to equal 0. So a little bit of maths here. So Q will be and that'll give me my answer. So I've got 5 minus 4 cos 60 over the cos of 70. So Q has a magnitude of 4.77 newtons. That's the size of that force. Okay, what about if we've got an equilibrium situation, a bit like that one, where there are two forces that we don't know? So same problem. 5 newtons there, 4 newtons there, with a 60 degree and a 70 degree angle. But let's say there's an additional force acting vertically, and let's call that P. Now, because it's acting vertically, I know it won't have any effect in the horizontal direction. So resolving horizontally, Well, my situation is going to be exactly the same as it was up here. So if I were to resolve horizontally, this force would have no effect. So I've got the same. I've got 5 newtons going that way minus 4 cos 60 and q cos 70. So horizontally I'd get the same answer here. So to work out P, I would then have to resolve vertically, and that means this 5 Newton force will have no effect because that's at right angles to vertical. So I've got P, and that's not at an angle, so it's just P acting upwards. I've also got this 4 Newton force, which has an upward effect. I don't know the angle between the verticals, so it's going to be 4 sine 60 or cos 30. And then coming down, I've got Q, and again I don't know the angle there. Well, I do, it's 20, but so it's Q sine 70 or Q cos 20. So it's minus Q sine 70. And it's in equilibrium, so they will equal 0. Now, I've got Q here, in fact I've still got Q here, so this time I'm going to do it properly. I'm going to store it and use it there and calculate the value of P. I encourage you to do the same. Pause and have a go. Okay, so I get P is 4.78 newtons. I hope you did as well. Okay, a little bit of practice. So firstly, some practice of equilibrium problems. So in the online version it's page 82, paper version page 111, same exercise, question 4, A, C, D and E. And then particularly for those physicists who have done this and probably have skipped through this video, can I suggest that you have a go at question 5 and 7, which is on page 82/83 if you're on the online version, and still on page 111 in the paper version. And they're just harder examples. And you all might want to have a go at those once you've tried the more straightforward ones. But yeah, that's just to make sure we're all okay. And we will leave that there. Please, if this is confusing, you must come and see me so we can sort this out, because I'm going to assume we've done this and we've understood it and we're going to build on it in either future lessons or future videos. Okay, take care.